My name is Linda Boyle, and I'm in civil, and I'm also your vice dean. But it is my pleasure to introduce my colleague, Andreas Riener. He's from TU Ingolstadt. He's here with his PhD student, Chantal, who is sitting here, and she will be giving a talk on Thursday. And so I just want to let you know, me and Andreas, we've known each other for many, many years. We both sit on the steering committee for the Automotive User Interface Conference. And there are papers that are due coming up, so if any of you want to go, it's going to be in California and Silicon Valley this year. At TU Ingolstadt, he is a professor, and he also is the academic director for the user experience design. So thank you very much for coming, and we look forward to your talk.
So, good afternoon. Mic is working for the online?
Yes.
I think so.
Yeah.
Okay, so what I prepared for you this afternoon is a little bit of insight and journey through the world of simulation, on-road tests, mixed reality. Just would like to provide you some insights of studies that we have done, and also looking a little bit towards automated driving and how it might also change the way of testing and the way of involving participants in the future. Before going into the topic, let's see, okay, the presentation and how it should work. Some acknowledgements to my team. So this is typically for us as professors, we are just presenting what our team is doing. We are steering, we are guiding, but all the hard work is done by the students, so I'd like to acknowledge my team. So this is part of my students. Chantal is over there. She is also one of my PhD students, putting all her life, all her leisure time into research. That's really cool to work with this team. So I'm just showing you a couple of things that we have done in the recent years. So just to maybe give you a bit of perspective what we are doing. We are human computer interaction group. Our research is most likely in the mobility domain or in the future mobility, but not only. So we also do some stuff with HCI in general. We are running the user experience design programs. It means we have students that are on the interface between computer science and design, which also allows us to have some cool visualizations, which you might not see in my presentation, but at least we have students that are also in this design area, and we are trying to make the best out of the two worlds. So we are human-computer interaction, and as Linda mentioned, we come from Ingolstadt, and some of you might know Ingolstadt is home of Audi, the headquarters of Audi, and also BMW, where Chantal is working at, is very close by, so it means automatically we have a lot of mobility research in Ingolstadt, or in this heart of Bavaria area, and also our university is logged into this. We are founded from requests by the mobility industry, and that's why we are doing a lot of mobility research, not only in my group, but at the entire university. We have programs, or many programs associated to mobility to some degree. It's not only cars, it's also aviation industry, it's also sustainability these days. But our research, and this was the main reason why I'm there, is that our university founded the Charisma Research Institute some 10 years ago. So Charisma stands for Center of Automotive Research. So this is the first three letters of Charisma, and the rest is safety, measurement, and so on. We have a lot of facilities, and that you see just a few highlighted. These are the ones that we are using in our research group. We are owning okay, this is not working on this kind of screens. We're owning a movement-based dynamic simulator. We have here a large testing facility with an indoor test track kind of. You'll see a video or some images later on. We have an auto test track, so we can combine simulation with real driving also in a safe and secured area. And we even have built a a mock-up in a trailer, so which means we can use this trailer and directly go to our test participants, being it school kids or elderly people that have no chance to come to our lab, so we just go there and do the studies at their whatever residential homes or anything like. Okay, but now coming into the topic of today's talk, and I just wanted to motivate it with a problem that we all know, at least if we are driving our cars, own cars, rental cars. There are a lot of assistance systems integrated or installed in the cars, but for a normal customer, it's often not really easy to find out how the systems actually works, how they are configured, what functionalities comes with these functions, and also what the reliability of systems like this is. And I'm starting with a very old example, adaptive cruise control, which is around since more than 20 years. All of you, or in all of your cars, in all of our cars, ECC systems are in operation. We know that they are looking differently, so not only the interface, but also how they are configured from different brands, different makes, different models. So the configuration means the gap settings that they allow, and also the configuration possibilities that you as a driver have. The thing is, as every system, it comes with limitations. And the limitations also change over time with different sensors that are used for the ACC systems and also other systems. But there is some limitations still evident today. So for example, sensor cannot look around the corner. If you have curvy roads, the system might fail. And also still stationary objects are a problem. But does the driver, does the user actually know about this problem? And I've just looked up some slides that Linda sent me a couple of years ago. So I have research from Linda, which she did also 15 years ago, asking ACC users and non-users if they are aware of the limitations of the systems. And the interesting fact is that back that time, and I'm quite sure that it's not changed that much, about 50% of people are not aware of the limitation of the system. This, of course, is not ideal. If you're using a system but you're not aware of the limitations, then this might cause troubles. So if the non-users are not aware, okay, they have not looked into the systems, but if the users are not aware of the limitations, this is really a problem. And why could this be the case? They might not have experienced the situation where the system just was not built for. Do you have a question? Or?
Yes. So this data looks like it's about more than a decade old. Do you have inclinations as to whether or not this number has changed? Has it gone up? Has it gone down? Is it roughly the same?
Yeah, so this is, we have not done similar, so we have not looked into this data, but just on the next slide, I show you a study that we have done on the AEB system, automatic emergency braking system, which is quite a newer system, and also the research that we have done is quite new. So we don't have any update on this, maybe Linda has, but also I don't want to stick to the numbers, just saying there is a problem in any system that we might use, that we are not aware of limitations, potentially. And if this goes down to 10%, still, it's too much. We should not use systems whose configuration is not known to us, or where we don't know where it might fail. Okay, so ACC, really old system, really old study. Let's come to something more up-to-date, an automated emergency braking assistant, which is said to increase road safety a lot. And the road safety typically is measured, amongst other things, with a star rating in, for example, Euro NCAP or US NCAP. So vehicle gets a star rating, and if you now you're about to purchase a new vehicle, you might look for a 5-star vehicle because this is something that at least induce a high chance of safety. It saves you, it saves other road users around you, but still, also for a 5-star rating, it's very difficult to say how safe or how reliable assistance systems on a 5-star vehicle actually are. Because there's also a lot of different configurations, just a lot of different situations. The sensor technology changes from vehicle generation to the next, and there's a lot of situations that not even have been tested in the test procedures to achieve that star rating. So one thing that we were interested in is, for example, if you look at situations, scenarios that are that you're confronted with when you drive in real road traffic, you have different times, different day times. There's maybe a reflection of sun, there is rain, there is fog, there is snow, there is reflections from the road surface, and so on. This is still only partially included in the test procedures. So we were interested in this, how this also might change the star rating or the reliability of these functions. And the second thing is also that the star rating or the NCAP procedures, they are renewed or updated every second year, every 2 years, which means for vehicles that are homologated 2 years ago, they are tested by the NCAP 2022 procedure. For that new makes and models that are homologated this year, they might be tested or they have to be tested with the 2024 procedures. And the procedures over time change based on changes also in the road infrastructure and also for new categories of road users. So for example, a couple of years ago, e-scooters came up. They were not included in older test procedures, but now included for sure in the newer test procedures. Also the systems are updated over time and find their way into the test procedures. So let's have a look in a study that we run for the Road Safety Board in Austria and Switzerland. And Germany was also included here, but did not pay. So it was paid by Austria and Swiss Road Safety Board. This study, and what we were looking into was, how does actually the star rating, how can we integrate the star rating, which is an idealized test procedure to some degree. As I said, there is no real rain testing, there is no nighttime testing in the test procedures, and also the test procedure they are straightforward in how the tests are conducted. So, for example, one of the tests that we tried to replicate is the so-called CPNC50. Car to pedestrian near side child 50%, and I've just tried to visualize how it's actually conducted. So we have here an ego vehicle, here number B, driving that direction. We have a pedestrian that is walking here from left to right. Partly occluded by this car. There's two cars that are just parked on the roadside. And the 50% says pedestrian and ego vehicle meet here at 50% of the width of the vehicle. Tests are conducted in a way that the ego vehicle B is moved with a speed of 20 to 60 km per hour, so in a 5 km per hour increment. The pedestrian here moves with fixed 5 km per hour if it's a child, 8 km if it's an adult, and 15 km per hour if it's a bike. And then you just count how often time the vehicle hits the pedestrian or the dummy or the target, or how often it applies the automated emergency braking system or assistant and saves the time. And then there's some tables you can look up which fraction of the test might fail, in which specific kilometer per hour range, and so on. And there's some complicated formula behind that gives you finally the star rating, but it's all transparent, you can look it up. Yes?
Quick question, on the pedestrian side of it, the pedestrian's always in constant speed?
Yes. Pedestrian is always in constant speed. Also the car is in constant speed, but the speed changes, so there's first test 20 kilometers per hour, second test 25, 30, and so on. Okay, so this is how it looks like then in our test scenario. And what we did is, so we had just replicated the standard test and then varied the speed a little bit. So we were interested also how much speed variation just a little bit outside the specified range might have an influence on the results. And then we introduced some rain, so we built up an artificial rain facility for our test track. And then we conducted this test also indoor, where we have a rain and also a fog facility, so we can generate fog, artificial fog, which has the same characteristics than real fog, just to see how much it affects the results. So here's some images of the tests we conducted, and we also used different vehicles. One manufactured in 2016, one in 2018, one in 2020. So we have 3 different vehicles. Also premium brands and cheaper brands, German-based and outside Germany produced vehicles. So different models. And then, so this is how it looks like. We did all the recording, the measurement, and so on. And maybe I'll show you just a few seconds of the video to show you how it looked like in the end. Just a few insights into the longer videos. It's not that interesting. So we had here, for example, a robot, a movement platform, and a target, which was equipped with the dummy, and then we generated some rain, some fog, and tested the function, and just measured if the system actually applied the emergency brake, if it hits the target, which happened quite often, or if it did not even apply the systems based on the configuration that we put into the system. Yeah, you see there's many targets were hit.
So the study was only done like one time, right? Like they didn't do it over, like the.
No, we did. So we repeated many times.
But the participant only like hit somebody once. Do you see what I'm saying?
So what we tried is we replicated one experiment so many times that at least 3 times the target was not hit.
Okay. Okay.
And then we did also some nighttime tests, also with rain. So we see it also here that sometimes targets were hit by the target. Yeah, I think we just got it how it.
The reason why I'm asking this question because I'm curious how people, like usually like when we do studies, once they hit somebody, even if it's fake, their behavior changes after that. So that's why I was wondering if that same person does it again.
Yeah. So that you mean the person in the car
Correct,
operating the vehicle.
Yeah.
So this one was only a fallback operator,
Ah,
did not even do anything.
I see.
We just
Okay.
looked into how the automated emergency braking
Okay.
system.
Okay. So it's really focused on the
activates.
system itself. Got
We
it.
only tested the system, not the driver.
Okay. Okay.
The automated emergency braking assistant should apply the brake
Got it.
whenever it sees a dummy that it recognizes as an object.
Okay.
And that's why we just had the fallback safety operator to stop the vehicle in case the assistant
Got it.
did not brake. And this was a trained driver. So
I see.
we only had one person doing
Got
all
everything. Got
all
it.
the driving tests,
Got it.
and we
Okay.
conducted more than 200 tests in total.
Got
So
it.
it cost 2 months' time also. Okay, so few results, just very general. What we saw is that, so star rating is one thing, but if you vary the setting, the configuration just a little bit, then you might achieve a worse result than the one that is just done in the official tests. What we also found is that bicyclists and also newer generation or newer forms of vulnerable road users like scooters or e-bikes, they were quite well recognized, in particular by the newer vehicles. So it means that this is all very good implemented, and the object detection algorithms also recognize these objects quite well. But what we wanted to say, or what my main message behind is also that, okay, you cannot just trust a star rating, say, okay, I have a safe vehicle and there's no need for me to watch traffic or so, the vehicle is doing it for me. This is not what's going to happen, because on the one side, the test procedure is limited. It's just a very narrow part of the entire possible situations that might occur in real traffic. And also the test conditions are idealized in a way that, it has to be reproducible, of course, but in reality, many more influencing factors play a role that never can be considered by such a test. What also is evident is that when we as humans drive, then we know that nighttime drive and nighttime plus rain, plus we're getting older, also nighttime rain for elderly people is really not easy to drive. But in particular in these situations, assistance systems should help. But right now, in most of the test procedures, this situation is not included. So you know you have a 5-star rating vehicle, but it only achieves the 5 stars during idealized daytime dry road condition, which is also not really ideal. Then another thing that whatever goes into detail already, that for one specific brand and model, let's say whatever, as I said, English is Audi time, let's say Audi A6 model 2020 with a specific whatever sensor setup. Even for this very specific vehicle, you cannot say that it always achieves the same rating, because whenever you go to the car dealer, they do some software updates, so they update the algorithm and nobody knows which algorithms runs on your actual vehicle. It's really hard, and so this is also what we saw. If you bring the same vehicle to the test track, it might result in different, or it might give you different results. And the least thing here is also when it comes to the interpretation of road safety or the interpretation of the star rating. Of course, we don't have to trust or should trust only the technical systems behind. We know that when we have black clothes or dark clothes in the night, then we as humans might have problems in identifying these objects, and sensor systems have the same problems, depending on the setup, for example. So it's always important also to be cautious and to be aware of this. Okay, so this is systems that are now in the car. Pretty old systems, and coming closer now to the automation, meaning higher levels of automation. We have seen ACC and AV systems, which are all level 1 systems, a very low level of automation. The driver has to drive and be aware and be active all the time. Question is now when it comes to higher levels of automation, level 2, level 3, systems are also on the roads already, how to test and evaluate functions on these levels. And we have some solutions, or we have done some different types of testing. So one is driving simulation. Driving simulation studies, this is something that is very popular. So you have a driving simulator, you implement some specific scenario, then you find out how well automation and humans maybe work together, and the next thing would be just to try to make an assumption how well this might be reproducible in real traffic. So here's an example of a system that we implemented back some time, just to see how well system and humans work together. With the lower levels of automation, we have not so fancy systems. We still have a lot of situations that are not so well handled, to be handled by sensors, for example, human behavior. So for human behavior, there's a good chance that a driver that is sitting in the car that still has to monitor and supervise the situation, which is the case for lower levels of automation, might have an immediate assumption what a pedestrian maybe would do, and the sensor and the algorithms running on the vehicle might have a hard problem in getting the same. So we often see such kind of cooperative systems where human and system on a car do some mutual decision-making processes. We set up a user study. Don't need to go into much detail about the number of participants and the exact setting, but what we did was, so the situation was a pedestrian crossing a street, no pedestrian walk, just whenever, on an arbitrary space. And we had a sensor set up on the car that just detected a pedestrian. It was the baseline condition. So it showed pedestrian detected, no explanation what actually happened and why the system thought that a pedestrian was actually detected. And then the person on the car had to decide whether to continue driving or stopping based on the situation that was shown on the screen. And then we had to do so-called confidence interfaces or systems. Again, pedestrian detected, but there was another level of detail here, namely an explanation what the system thinks that is going to happen. The pedestrian is crossing the street. In addition, a confidence level was shown on the HMI. And the second configuration was pedestrian detected, plus the information crossing the street was assumed by the system, and instead of showing a concrete level of confidence, it was like a progress bar type of visualization. And we just were interested in how long it takes for the human counterpart to interpret, so detect the situation, interpret the situation, value with his own decision-making things, and then come to a joint decision with the system. Yeah?
How do you get confidence?
How we get confidence?
Mm-hmm.
Yeah, so this was kind of a fake system. It was not a real system, so it was just programmed. I'll show you later on. We had 3 different confidence values: 20% confidence, 50% confidence, and 80% confidence. We were just interested how much it plays a role, how confident the system is on a certain situation. But there was no real there's no real algorithm behind it. It was just a variation of the conditions here. So the experiment was built up like this, a simulated drive at a certain position. The scenario was detected. Participants valued the situation, came to a decision, a joint decision making with the information shown on the display, set a reaction, and then the situation was cleared. So the maneuver was executed, either stop the vehicle or continue to drive, and then it was presented if the decision was correct or was wrong. This is how it looked like in the simulator. So we have here kind of a head-up display, the pedestrian. Here we see 50% confidence that the pedestrian is going to stop, not cross the street. We see the decision of the participant to stop in this case, or to go on, continue, and then the situation was clear. For the second time, so the participant pressed the button on the steering wheel, either left or right, to enter a decision in this case. The result was, so the baseline situation where we had no explanation compared to both confidence HMIs with an explanation, and the confidence level is that this is nothing unexpected. Decision time when with no explanation was shorter compared to the confidence HMI. Of course, you have your own interpretation of the situation, and then you have to value how confident the system was, and you have to come to a joint decision. So it takes longer time. This is nothing unexpected.
Excuse me,
When
sorry.
we look into the concrete, yeah?
Sorry, quick question. Interaction time is just time to press any button.
Yes. So interaction time was the time to come to a decision. When we look at the different confidence levels, so we have here light blue is the 20% confidence, so the system has a 20% confidence in its rating, 50% or an 80%. Then we see, of course, the higher the confidence value is, the shorter the time to come to a decision. For 20% confidence, we see a large variation on the one side and a very long decision time, which is also not really unexpected. But the interesting thing is when we compare the confidence bar versus the confidence percent, that people did not like the concrete percentage values. So they took longer with a percent value, and this is also something that we might show like a progress bar thing, not a concrete percentage values, even if we are possible, or even if it's possible to compute such a value, it's better to keep it abstract. For the 20% confidence value, there was this large variation. Of course, many participants needed very long to decide. Okay, I rate it differently, the system is not very confident in what it's projecting, so there's also some back and forth thing. So better not to show at all if you have a very low confidence about the decision or about the situation. So it's only makes really sense if the confidence level is high to support the human driver. And this is also something that keeps going when the system are learning to maybe this AI algorithms, which are quite popular these days, to improve on the confidence value. So the on perception plus the confidence information, when it's coherent, then the decision time can be a bit lower than in the case or than in the situation with no information at all. But the main thing is also that we just wanted to see how systems and humans operate together. And if you think such an experiment in a real traffic environment, it's dangerous because you have pedestrians that might have to step on the road and that might be hit by the vehicle. The question is always still, how much can you replicate the results for reality, right? So it's always simulation, there's no real harm for nobody, and it's also questionable how you come to the confidence level, which was also a question from some of you. Yeah?
Yeah, I'm just curious if you asked people about their sentiments, or did you ask them how they felt when the system had very low confidence, for example?
Yeah, so people did not like this information with a very low confidence value. That's also the consequence that later on it's better to not show it all, because if you cannot be sure that the system gives you the right supporting information, then it's of no value. It might even have a negative impact if you trust the system. Still, if the confidence level very low, but still some people might follow the decision that the system was giving them, which result then in a bad situation. So that's why I'm saying, if the confidence level or the competence of the system is very low, and I'm not saying 20% only, but maybe even below 60% or so, so parameterization is something that we're working on, then it's better to not show it all and just ask the person so if it's in a cooperation situation, what they want to like, or just be on the safe side and break. But we also know that wrong system behavior might lead into switching it off. This is something that we have also seen in systems that are in operation, like the AEB system, the automated emergency braking system. This is always, or yes, there are a lot of situations in the earlier times of system availability that these systems just apply the brake without any particular dangerous object. And then people tend to switch the system off. And yeah, if you have an assistance systems that is switched off, then it does not count either. So it's very hard to have this parameterization, trust, overtrust, mistrust, experience of situations that are not really explainable for the human driver. So that's nowadays something that is really a lot of research is put into this, in particular when it comes to a move from a traditional deterministic system behavior to a non-deterministic black box behavior, which you have with AI systems that are integrated. So careful parameterization is important. And also parameterization for the individual is important, because some people, so if you have a lot of driving experience, you might rate the situation different than a novice driver that has also not the capabilities for situation awareness, for rating every whatever traffic object correctly and so on, for having no concrete or whatever less experience in rating distances and potential behavior of persons in a situation. So this is very important. But driving simulation is still an important component in the entire ecosystem of checking out system capabilities, and even in the introduction of new system. Driving simulation can be done at a very early point in the development, so just to see also if people accept such systems or not, and what should be configuration and what should be parameterization before bringing it further towards production cars. So driving simulation. We saw that simulation, and this is something that is known also for a long time in research, simulation never replicates reality. So we thought, okay, let's go one step further and try to do some driving tests on a test track, which is feeling more natural for the test participants, but still by conserving safety for every one that is involved in this test. And actually, we were looking into level 3 systems, so little bit higher in the automation. Level 3 systems are already on our roads. So this is nothing that is far in the future. They are already on the roads, but still we need to improve the systems, and we need to see how well they are perceived and by the participants, and how good the systems actually are configured in different scenarios. So I don't know how much you are into these levels of automation or automated driving at all. There is 5 levels, or 5 levels plus level 0. Level 0 means no automation or just manual driving. Level 1 is ACC AV systems, and level 2 is a combination of longitudinal and lateral control of the vehicle. At these lower levels, 0, 1 and 2, the human driver is still still has to monitor the drive all the time and is responsible for every decision that is made by the vehicle plus driver. In the higher levels, starting at level 3, there are situations where the driver can do different things, so-called non-driving related tasks, NDFD, but still the vehicle is not capable of doing the entire drive. So there might be situations coming up where the vehicle asks the driver to take over. And these are so-called take-over requests. The vehicle says, there's a problem, I can't solve it, driver please help me take over and drive manually. So this is the case for level 3 systems. In the level 3 system, so the takeover, or actually being capable to take over on a request by the vehicle, is the situation or the point in the drive which is mostly researched so far. There's different timings that are required to be capable of taking over. Of course, it depends on the traffic situation, it depends on what the driver was doing before. Was he reading a book or working on his iPad or handheld device, or maybe just looking out of the window, daydreaming? So this is all affecting the takeover time, takeover reaction time. When we look into research, then we find timings that start by about 3 seconds. So from the point where the takeover request is issued until the driver has the hands on the wheel and being capable of driving manually. Still, this takeover request, so this takeover time of 3 seconds, does not necessarily include be capable of having full awareness of the situation. So situation awareness is something that might take 5 up to 10 seconds in addition, but still you're on the wheel, which means that the responsibility is already transferred back from the vehicle to the driver, and this is the only value or the only time the manufacturer and the legal staff is interested. So take over time, and then post takeover control. This is what I mean. This might take up to 40 seconds to gain really full awareness of the situations, being capable of solving everything, knowing what's going on, what has been gone on, what was the problem of the vehicle. But so these upper boundaries, typically it's not considered in research because of the responsibility, which is the main problem. Also, we know that all of this research, or most of this research, was done in simulator studies so far. Again, we had a driving simulator, either a static one or a dynamic one. There were some artificial scenarios, and then time was measured until the takeover was issued, until the takeover was completed, or hands on the wheel, or whatever, feet on the pedals. So this was mainly obtained in driving simulator studies. Also in our team, we run different driving simulator studies to measure takeover timing. But then, as said before, when you try to interpret this for a real vehicle that has permit to drive on the road, like the Swedish drive pilot or other level 3 systems, timing might change, and what typically is done, you have a factor like 3 the time, 4 the time to be on the safe side, but drivers might not feel comfortable with a long takeover request time ahead the actual critical situation. So it needs to be parameterized also in a way that it's accepted by the drivers. Because if you experience some situations where the takeover request comes way early, the actual critical situation, in the next takeover request you might not take over on time because you think you still have a lot of time to go before the actual critical situation might happen, and then it could lead into a critical situation. So what we did is we set up an experiment on the test track, and we used the car, just a regular car without any particular assistance system. We installed a so-called driving robot on the car, which you see here. So there's hydraulic actuators actuating the pedals, and there was another robot system moving the steering wheel. So this way any normal production car can be turned into some kind of automated vehicle. We put the pedestrians on the driver's seat. They were confronted with a driving situation and a non-driving related task on the smartphone. We put them on the test track. They had to drive or were driven basically on a closed loop drive with some curves at a maximum speed of 30 kilometers per hour. And we had here a platform that moving a balloon target on either of these 2 lanes. And then whenever the participants completed the next round, at around this position here, takeover request was issued, 7 seconds lead time we implemented, and then the participants had to steer the car manually in either of the 2 lanes to avoid crashing into this target. This was combined with the non-driving related task, which was a simple reading span task. So there was a sentence presented on the smartphone, and the semantic correctness of this sentence had to be rated. This was the one condition. It was visual motoric, just putting or pressing a button, and the same task was also presented as an auditory task with voice interaction, just agree or reject. And then we had, in addition, the timing for the takeover request. This was our second independent variable, with one aspect was, okay, the takeover request is issued whenever it is required to issue it, meaning also in between the current task that had to be solved. And the second variant, the second level, was issuing the takeover only between tasks. So meaning after one task was completed, so maybe you can wait half second more before issuing the takeover request. The task was completed, which means also less cognitive demand for the participant, for the person, because in this first level, you're midst in a task, then the takeover request comes, you take over, you drive the car, and you get back to the task, which induces a so-called resumption lag. So you have to get aware what I'm doing before, kind of, which causes a bit of cognitive stress, which is also something that we would like to avoid, of course, in a real situation. Again, here a couple of seconds of a video, how it was actually implemented in the car, automated drive. Then here we come close to the last curve. Takeover is requested on a display here in the center area of the car. Participants have to grab the steering wheel and have to steer the vehicle to avoid crashing into the target. We did all the measurements and recruited 22 participants here that run into a randomized experiment with all the 4 conditions, so meaning the 2 tour conditions in between and after the task, and the 2 levels of presenting the actual task, one's visual with physical or motoric feedback, and the other one auditory with voice feedback. What we found is that on average, our take over time was just about 1 second, 1.12 second, which is compared to the simulator studies, 3 seconds, so it's way lower. The second thing is, can drive us in this test track setting, which is also somehow artificial compared to real traffic, because there's also no real danger involved, but it feels more dangerous than a simulator. Can they respond to the tour safely? So the one thing is, that the takeover request was really handled very quickly. So it means that people were more aware of the situation and of the problem, maybe also getting hurt than in the simulator. And on the other side, still 10% of test cases or participants produced an accident, and in about 30% of all cases, there were lane exceedances. So it means, so they grabbed the wheel rather quickly, but then were not able to complete the task really safe. And this is maybe shown here on this graph. See here the 2 lanes. Blue is kind of the safe path, and we see here one exceeding quite a bit, and many others also had to counter steer. So it means that it's way better to do it in such a configuration than in a simulator, but still the question is, are test track experiments beneficial compared to real driving? And I would say, yeah, they're more beneficial than just the simulator studies, but it's also more efforts to put into to run such a study. But in terms of configuring and parameterizing a real function of the vehicle, I'm definitely in favor of doing such experiments on a test track compared to simulation. And the next thing is, so we have simulation, we have test track, and nowadays also when it comes to more and more situations and also to avoid safety issues, nowadays mixed reality environments gain more attractiveness, and this is also something that we did because what was the logical next step then. So we had first this pure simulation, we had the test track experiments for the road safety board, we had our own takeover request experiments on a test track, and we saw that it's highly complex and high effort required to run the experiments to get kind of close to reality simulation, close to reality results, sorry. And now with the capability of virtual reality and also the capabilities that we had in our research center, we tried to bring together the best of both worlds in such a mixed reality environment. So we had on the one side, we had the 100% real proving ground testing with all the equipment brought into the test facility. On the other end of the spectrum, we have pure simulation, not even involving test participants maybe, just using algorithms and functions implemented in software. And then we can bring both worlds together, having physical objects, physical car maybe here in the test environment, but bringing in simulated objects in one and the same environment, so to be able to test systems. So for example, a real sensor on a real car against a situation that is just simulated in software. And this is how it might feel. So we have here a real vehicle that is driving on our auto test track, for example. It's sending position data to a simulated vehicle that is driving in a virtual reality environment, or like a Scala or Unity environment. The virtual vehicle is equipped with a sensor, with a virtual sensor, a sensor model, and once the virtual sensor model detects an object in a virtual environment, it exchanges data with the real vehicle, and the real vehicle applies the brake or moves the steering wheel, for example. So this way we could replicate tests, run oftentimes in a very safe and efficient manner. And this is maybe the last thing that I'm showing. Here's the configuration, but I'm giving also some insights how it finally. So what we can finally do with this mixed reality environment. Let's see. Just move a bit forward. Yeah, so this is maybe showing. So we have a person wearing a motion capturing system and a virtual reality headset. We have a real vehicle driving on a test track, sending over its position data to our central simulation. So we have the real vehicle replicated in our virtual environment. We have the sensor system, and this is the camera of the virtual vehicle, seeing here a person maybe starting to walk or across the street. This person was actually mimicked, or a replication of the pedestrian that is walking here in the virtual reality environment. And once the sensor in the virtual vehicle detects the pedestrian object, it applies the brake in the real vehicle. So this is kind of how it was implemented. And I'll just show you once again how it looks like. So this is also a way of reproducing tests in an efficient manner without causing safety problems for any of the involved parties, and just trying to find out how well functions work. So like close the loop to the NCAP test that we had before, but now in a very efficient, more efficient manner, but also using either software sensor models or using the real sensor on a vehicle with a vehicle in the loop integration. Yeah, I think I stop here at this point.
Thank you,
The
Andreas.
the next level will be then a digital twin approach. Yeah, I think that's all.
So, yeah, I apologize for 5 o'clock, because I know some of you may actually have some classes, but, and there's been a lot of questions that were asked throughout the presentation, but if there's any additional, if you have time, I mean, I'm happy to stay. So if there's any other questions that you might have, please raise your hand.
If there's online participants, they can also ask the questions in the chat. Just
Oh, yeah, so
put
there's a
in
question here.
One of your findings I thought was very interesting was that different vehicles, so from the first part of the research, to recreate the safety testing, you found that different models of the same vehicle could have different performance results based upon the configuration of the sensors or even the software, which updates, semi-regularly, and that is essentially a black box to us researchers. How much level of standardization and replicability is necessary in order for these technologies to achieve widespread trust from society and broad adoption?
Yeah, so this is a question not so easy to answer because it has been. So the thing is, the variation might not be. So it might easily be replicated in a study like the one that we did, to see what really the difference is. If you are participating in a real world environment as a pedestrian, for example, you might not see what really the variance is. When we now think a little bit further in the future with automated systems, with AI algorithms, then the whole thing gets even more worse than it is now, because when you have an automated system, like think about all vehicles are automated to some degree, then not only the pedestrians or the vulnerable road users need to have trust in the system or need to know how they kind of work, but also all the rest of the traffic objects need to know how the opposite is going to react on a specific situation. And this is something that is really not so easy to maintain, because on the one side, every person has its whatever kind of personalized driving style. Now in manual driving, we all might want that our vehicles in the future drive also like we want to be driven, like more conservative or more aggressive, in order to whatever accept technology and use it finally. But as long or as soon as there is a parameterization or individualization of driving functions, the opposite, it's hard for the opposite to know how a vehicle might behave. So you might be able to exchange data, you might be able to communicate your parameterization to the opposite, but it's a lot of data processing involved then. So the ideal world would be having one function or having a function configured, and then all the vehicles have it installed or implemented the same way, across makes, across models, across countries, whatever, is not what we really would like to see, and also not what we will see.
Maybe
So
just maybe one more question, and then this way people, if they have to go.
I don't know if there's any
Oh,
online.
go on the chat, it looks like there's might be a
No,
question.
there's no one in the chat.
There's two, but there's two.
Yeah, so this is
it's
Elizabeth
different?
just,
Okay.
Elizabeth just
Oh,
putting
okay,
some
okay, all right.
comments that people can
Yes,
ask
because I know that some
online.
people have to go, so I don't wanna, yeah, did you have a question?
Okay, I just have a more basic version of that question, which is how many more, if we're already seeing this much trouble with level 1 automation, how many more kinds of tests do we need to make sure level 5 works?
So formally we had these endurance tests. So, and maybe Chantal, she knows way better because she's working at BMW, which means that for every function before being approved, you have to provide whatever, some million test kilometers to make sure that it's working properly in every potential situation. Still then you don't get the really critical situations.
You don't get edge cases.
Nowadays, so the one thing is that Euro NCAP has also realized this, because not only Euro, but also the different assessment protocols. And what they are doing, they introduce from 2030 on, they introduce instead of these very punctuated concrete test points and cases, they introduce so-called range tests. So this is one way towards solving this problem. And the other way is we cannot really do all these tests in reality. So there is simulation, edge cases you mentioned, so identification of edge cases and testing these in a simulated environment. So this is the solution that is currently followed. And of course, if you have standardization in the sense of every vehicle behaves the same, you might argue, yeah, in a level 5 scenario, you're not longer driving, so it's like a taxi or so. You can do whatever you want, so travel time or speed doesn't really matter. Yeah, so this is an argument. Still not sure if everybody would like to hear that this might be the solution, and it will also not come that way.
There's also something which is called a positive risk balance, at least BMW is using that. So primarily we're looking at how many accidents are happening without the driver assistance systems, and we're having a positive risk balance if less accidents are happening with the systems. And for us, that's a really standard.
That's a real world measurement though, right?
Yeah.
Okay, so you would only find that out after you deploy level 5?
Oh no, before a system enters the market, we have
Okay.
internal tests, and every system or every final vehicle setup will run 1 million test kilometers before being exposed to the market.
Okay, but that.
At least BMW does that. Can I promise about, I don't know, Tesla?
And then you can think about that, because she's gonna be giving a talk on Thursday.
Oh,
So you can ask her some more detailed questions about the automotive industry. By the way, there is a question here It's basic, so Jason Ding, he wants to know if he can maybe share your paper titled AR/VR pedestrian simulation in the real world. He's interested, and maybe other people may be interested.
Yeah, sure, I
So if
can
you want to
just,
share it, I can
I
have
can,
Con
I can
post it.
share the slides and I can also share the
Okay,
papers that I
great, thank you.
mentioned, so maybe just send it to Elizabeth.
Sure. Did you have a
Well, I
comment?
was just gonna say the video, I think, if Elizabeth discussed with you, we usually will post the video on YouTube after, so we can even post some links in the comments.
Oh, how
Yeah,
nice,
yeah,
that's great,
sure.
so this is
So we
gonna be
can
on YouTube?
Yeah.
If you're okay with that, yeah.
Yeah, I think it was recorded, so
Yes,
yeah, we
yeah.
can just
Okay,
add
great.
the links.
Oh, good. All right, thank you so much, everybody, for coming and for your great questions. I know we went over, but there were so many questions in between that it was great.
No, that's
Thank you,
fine. So-
guys. Yeah.
I'm still around, so if there are more
Yeah.
questions, we can have them.
I have a specific